Hello, today we're going to look at NX CAE. What you see on the screen is a picture of a door shelf for my refrigerator. As you may notice, right through the middle of it there's a large crack that goes almost all the way across the door shelf. So the issue is that this thing has cracked, and trying to determine what happened to it, my best guess was that my children were closing the door, and rather than use the handle, they were grabbing this door shelf and closing it and cracking it, or eventually cracked it, as the engineering of the door shelf probably did not take into account the fact that there would be additional loads due to people grabbing and pulling the door shelf. So actually had this door shelf replaced, and the one that you're looking at is a second one that cracked as well. And between getting the first and the second door shelf, I made a clear point to my family to make sure we don't close the refrigerator by the door shelf. So the conclusion I've come to at this point after the second one cracked was that it's actually just poor engineering, as it wasn't really set up to handle the loading of just having items on that shelf. I was kind of disappointed in the quality. It's a pretty new refrigerator, a little over a year old, and I've already have two cracked door shelves as part of that. So how does that relate to NX CAE? Before we get into that, another item I want to mention is cost savings and what companies are doing to save costs. So the example on this slide shows how Chrysler is doing things to save money. A recent article points out that they've saved $100,000 a year by letting the snow sit on the top level of the parking deck. They've done some things by removing clocks from the walls. They found out that it was costing them $20,000 a year in batteries and changing the time, the manpower used to change the time. They've removed light bulbs, and probably a lot of us have seen that in different buildings where maybe half of the lights or a third of the lights are removed to reduce electricity costs. They've adjusted the heating. So companies, this is an example of Chrysler, but a lot of companies are doing things to try to save money, and NX CAE ties into that as well. We can help your company save money by doing things like eliminating the number of prototypes you do in your engineering work, by analyzing a product up front and getting a better product with lesser prototypes. By also producing a better product, it will reduce the number of product recalls that you'll see. Again, very expensive to recall a product and have to make changes to that product. And the third thing that NX CAE analysis can do is reduce or improve your time to market. Getting a product out to the market faster, being the first one to market, definitely can give you a bigger market share, and again, in most cases, save you engineering costs as well as increase your sales. So let's start and take a look at NX CAE and an analysis that we're going to do in NX CAE, and that is going to be a case analysis. And this is a plastic case. And what we're going to simulate with this plastic case is we're going to, you can see in this lower area there's a couple of tabs there where this plastic case fits onto another part, and we want to find out if it's going to break under a 15-pound load that simulates this snap fit of it going onto another part. So we're going to jump into an analysis quickly of this part. So we're going to set up a finite element model here. And the first step to do that would be to select our solver, which is our built-in NX Nastran solver. So, and the type of analysis we're going to do for this model is a structural analysis. First thing I want to do is I want to apply a mesh on this part. and I'm going to use tetrahedron elements for this model. I can have the software suggest the mesh size. I can type in my own value. I can take a preview of what that mesh size is going to look like before actually generated on the part. So let's go ahead and very quickly generate the mesh that'll be used to do the analysis. You can see what that mesh looks like. It is pretty coarse, but for our purposes of demonstrating the software today, it should be adequate to give us some decent results. Now, the thing that I need to do also, in addition to generating the mesh, is I need to assign a material to the part. This particular part that I just selected is made out of a polycarbonate material. As I work my way down through the standard material library that comes with NX, you can see I have a polycarbonate material listed there. And let's just take a look at that briefly. One thing I want to make a note of is the yield and other properties that are associated with this particular material. And the yield strength is 62 kilopascals, or 62,000 pascals. So we certainly want to stay well under that yield strength value that we have for this particular material. That's kind of going to be our design goal. So let's take a break from the demonstration for a second and move back and talk a little bit about NX CAE. One of the ways that we improve time to market, we improve your product, is the abilities we have in our meshing area, which I showed you a very quick mesh there. But quality mesh can be a time-consuming process, especially if you're not using NX. This example model here, it took about 2 weeks to go in and clean up the model, which is the topology abstraction and cleanup part of it, and generate the mesh. Whereas in NX, since we include auto cleanup in our meshing process, we were able to take the same part and mesh that part in about 2 minutes. So that's a great time savings, and again, time is money in the engineering process, and a great money savings as well. So let's move on in this process into the next part, which is actually analyze the case and evaluate the results on that case. So we want to apply a fixed boundary condition, and before I do that, I'm going to go ahead and turn off the display of the elements just to make it a little easier to see. So I'm going to do a fixed constraint on these bosses. 4 surfaces I'll select here so that they are not moving in the analysis. And then the load, as I mentioned at the beginning, is going to be a force load on these tabs located in that area, a 15-pound force that will apply in the negative Z direction. You can see the arrow pointing downward there, and when I apply that, you can see the display of that boundary condition. So that's really all the setup that's involved in this model. Let's go ahead and quickly do a solution. And Nastran solver has started, and we will get a graph of the solution as it converged, which it has done already. So let's take a look at the results. Once we have solved the model, we have results available, and the ones that we're most interested in are the stresses. And the stress value that we're looking at were in units of kilopascals. So let's set the results from English units over to kilopascals, and then we can compare our results versus what our yield strength of the material was. And as we do that, we can see that the actual highest stress value is about 124,000 kilopascals, or pascals, or 124 kilopascals, and our yield was about 62. So we're about double the yield point of the material. This part would definitely be breaking, and it looks like in this area of the bosses, as this pushes down, this part would break just on the bottom side of those two bosses. So the design as we currently have set it up is not going to work. It's going to fail, and we need to do something to try to address that issue. Okay, so let's take a look at redesigning the case to try to fix the issue with the part breaking. So before we do that, let's talk a little bit about solution speed. We had a customer that was looking to improve solution speed. Improving solution speed would enable them to increase the number of simulation iterations that they would be able to do, which will reduce the time to market. It will also reduce the number of prototypes that they can do if they can successfully have more simulation iterations performed. The potential solution they were looking at was switching from the Ansys solver to NX Nastran, and what they found was that the Nastran simulations took 25% of the amount of time that the Ansys simulations did on the same model. So our solver, NX Nastran, can greatly reduce your overall simulation time, especially if you're dealing with large models, which many customers are. The damping technology gave us this quote that NX Nastran was faster, and it also came with the best support. So a faster solution will help, again, eliminate prototypes, improve time to market. And let's go ahead and look at that process of doing some iteration. So we're going to go back to our CAD model and make some changes here to try and eliminate the issue that we had with the potential breakage of the part near the boss area. So what I'm going to do is I'm going to make some changes to the part. The first one is going to be, the first thing I need to do is I need to promote the part so that I can make changes to it. And then what I'd like to do is I got some information from a thermal analysis that I need to widen these holes that are in the model in order to get more airflow through this area. So I'm going to make that change first. I'm going to do that just by resizing a particular face. You'll notice when I select that part, even though this part came in as a step file and has no history associated with it, using synchronous modeling tools like resize face, it automatically determined that these four faces all were built from the same feature and are the same size, and it by default selected those simultaneously to allow me to make changes to those in one command. Now if I turn off that selection, I could move one of these individually, but in this case I do want to widen all of them, so I'll leave that selected, type in a new value, and then you can see it opens up those air holes very easily to allow more airflow through the part in that area. Now, on the structural side, I wanted to stiffen this part up to try to reduce the stresses that we have. And the way I'm going to do that is I'm going to make a copy of this boss, and I set my selector to be boss or pocket faces. Grab the boss, select a direction, in this case, that vector direction is going to be in the Y direction, it looks like. And then I can either click and drag the boss, or I can type in the value for the new location where I want it located, which is going to be 2 inches from the current location, about in that area there. And since I have paste toggled on, when I hit OK, it'll actually make a copy and paste that feature into its new location. So my plan is to copy this boss here, basically making a second boss, fixing this when I go back to my analysis, and see if that doesn't reduce the stresses by making the overall part stiffer. So now that I've made the changes in the CAD side, all I have to do is go and load my finite element model, and you can see the ghost area here where the new geometry is. You can also notice that this update mesh button is active. If I click on that, it will remesh the part based on the original parameters that I defined, including those larger holes, this new boss, and the same material properties that I defined, but it's now very quickly updated in NX CAE. And then the last thing I need to do is update my solution. And what I'm going to do is I'm going to clone the original solution or make a copy of it so that I can keep my original results in case I want to compare those later. And we'll just call this solution with second boss. We'll call it that. I already have my load updated on that solution. I do need to update my constraint, so I can just double-click on the constraint and add a second fixed constraint on the two bosses that I've added to the model, and I'm ready to solve. And I'll quickly go ahead and do another solution. Okay, and once again, very quickly, probably before I can even pull the graph up, the model is solved, and we'll take a look at those results. And again, using the same results that we had before, which was, let's just do megapascals. So we're looking for something under 62 megapascals, and now we're down to 21 megapascals. So first time I looked at in kilopascals, which would add 3 zeros to that, so 21,000 would be what we were looking at if you view that. So these results are good, but in talking to my designer, it turns out that the redesign, even though it now satisfies my analysis requirement, from the design side, he tells me that it turns out that they need to run some cables in this area, and I need to take the boss back out of there and find another solution to that. So now what we're going to do is we're going to go and redesign this thing again with a boss in a different location. So we'll go through the same process again. We'll go back to the CAD model, and there's a number of ways we can get rid of that feature. Probably the easiest way would be to go in and delete the face, pick that same face that I had before, and just delete it off of the model. And then what we're going to do, we're going to put the new boss, we're going to make a boss again this time, and we're going to put it basically in the middle here so it's not in the cable area. So before I do that, what I'm going to do is I'm going to grow that little tab that I have in that area up a little bit. So let's grow it in the Z direction, maybe at that point right there, and I want to pull it up just a little bit, until, not that far, but a little bit until it reaches that face, just to make it a little bit stronger. So let's maybe type in a value here of 0.15 inches. And we'll hit OK, and actually didn't quite work right. I went the other direction there. So see if we can fix that. So what we'll do is we'll go into modeling, and you can see any of these things that I've added to the model show up as features. So I made a mistake on that last one. What I can do is grab that and flip the direction on it, and now it's pointing up, and correct it so that my tab is facing the right way. So that's the first change I want to make. The second one is the same thing that I did before. It is just going in and copying that feature that I had and moving it this time just to a new location. So I've got my selector set to boss or pocket faces. I grab the feature. I want to move it in the Y direction. We can pivot it the center point here, and the distance this time is going to be 1.24 inches. And we'll put that in this location, except what I'm going to do, a slight change this time around, is I'm going to delete these extra little ribs that came in with the move, since I already have this other tab there that it's sitting on to give it additional strength. So I don't really need these small ribs. I'm going to set my faces. I'll select both of these ribs, delete those, and then we're ready to go and do our updates. So the first update that I want to do will be the mesh. once again, see the information window that our part has changed. We'll see the ghost image, and then very quickly we can update our mesh. The second change that we're going to make is to actually update and create a new solution. So we'll clone our second solution, and in the cloned solution, maybe we'll rename this to solution with boss on tab, call it that. And again, the only thing we need to constrain or change is the fixed constraint to include these two features, these two bosses, and we're ready to solve this once again. So we'll go through the process one last time and see if we have a satisfactory solution. And we'll watch the model converge during the solution and take a look at the results. And this time, I want to make one small change as I look at the results. One of the reasons I cloned these solutions is so that I could keep all three sets of results there for me. So what I want to do is I want to set up maybe 4 viewports and look at the results side by side in each different viewport. So we're going to start with the model number 3, and we'll put that result in the bottom left viewport. We'll go back to our second set of results. We'll put that in the upper right viewport. In just a second here, I'll make these so they're all visible. And then the original result that the stress was too high, we'll put in our front left viewport. I'll synchronize these views so that they all have the same view. And let's auto scale those. And let's see, very quickly, now I can see these results. The other thing I need to do is select all these and let's set the result to be megapascals again, which I think is the easiest to see in all 3 of those. So we've got 123 in the upper right, or upper left in solution 1, 21 with solution 2, and the one we haven't looked at yet, we just solved. The stresses went up a little bit, but they're still well under our 62. They're 24.3 megapascals. So our new solution is a satisfactory solution, and we've done the redesign in a way that will be satisfactory from an engineering and design perspective. So we've shown within NX CAE, again, you can eliminate prototypes by doing analysis on the computer before or during that process of building prototypes. Since you're catching errors early on, you're going to reduce the number of product recalls, and your time to market will be shorter than had you not done the analysis in NX CAE. Another issue that we didn't spend a lot of time on in this particular model but does happen automatically is geometry cleanup. It's also a big part of doing an analysis, and we spent a lot of time in the development and spent a lot of time in NX making it easier to clean up very detailed CAD models so that they're easier to mesh, so that your mesh doesn't fail, doing things like eliminating slither areas, tiny edges, and this particular example, they were looking at geometry cleanup that took about a week worth of time to do in Ansys. In NX, using heel geometry and the other automated cleanup tools, we're able to do the same model in about a half a day. So you can, another area that we didn't focus this demonstration on a lot, but it's very important to many people, is the geometry cleanup, and that could be either dirt or geometry or just many CAD details that aren't needed in an analysis. You can see here about a 10-to-1 improvement in amount of time it spends to clean up models when you use NX CAE. So the fact that you're also having using an integrated system means that you don't do any translation, and having associativity where everything automatically updates like we showed in the demonstration can also save you 2 weeks, giving you a total time savings on this particular project of about 6 weeks worth of time. So that concludes the presentation for today. Thank you for